What if everything you've ever believed about reality is wrong? What if the universe is not made up of countless independent pieces, but is instead one vast, interconnected entity where nothing truly stands alone? At first glance, that sounds like philosophy, maybe even science fiction, but some of the deepest ideas in modern physics hint that this might actually be the case. Think about it. When you look around your room, you see separate objects: a chair, a table, your phone, your own hand. They seem solid, distinct, and isolated, but the more closely scientists investigate, the blurrier those boundaries become. At the quantum level, where the rules of physics become almost unrecognizably strange, the very idea of separate things begins to collapse. This video will take you on a journey through that hidden side of reality, from the ordinary world you experience every day, to the bizarre behaviors of subatomic particles, and then to radical new theories suggesting that the entire cosmos could be a single quantum object. Along the way, you'll see how everyday matter hides mind-bending mysteries, how science itself is facing a crisis that forces us to question old assumptions, and how some researchers are daring to connect the puzzle of consciousness to the fundamental fabric of the universe. But to begin understanding this, we first need to explore the foundation of how science has traditionally tried to explain reality. The idea of breaking things down into smaller and smaller parts. Look around you. The objects in your daily life seem straightforward. A chair is just a chair. But science has shown us that this solid object is actually built from layers upon layers of hidden structure. Start with the macroscopic view: wood, fabric, or metal materials we can see and touch. Break it down further, and you get cells and fibers, the microscopic building blocks of living and non-living matter. Dig deeper still, and those fibers are made of molecules, combinations of atoms linked by chemical bonds. Zoom inside an atom, and you find protons, neutrons, and electrons. Finally, split protons and neutrons, and you arrive at quarks, the current limit of our experimental knowledge. This method of understanding, taking something complex and explaining it by its parts, is called reductionism. It has been the cornerstone of science for centuries. Reductionism gave birth to chemistry, led to the creation of modern medicine, allowed us to invent electronics, and ultimately delivered the standard model of particle physics, a kind of periodic table for the fundamental particles of nature. But here's the twist. Reductionism may not tell us the full story. Imagine trying to understand a symphony by analyzing every individual note. You could catalog the pitch, the rhythm, the duration of each sound, but you'd miss the meaning of the music itself. Similarly, breaking reality into quarks and electrons tells us a lot, but it might blind us to the larger patterns that only make sense when seen as a whole. This realization sets the stage for quantum mechanics, where the rules are so alien that they challenge our deepest assumptions about what's real. If reductionism gave us confidence that the world could be understood piece by piece, quantum mechanics shattered that confidence. Because at the smallest scales, reality doesn't behave like anything in our everyday lives. Take something simple, a light switch. Normally, it's either on or off. But in the quantum world, particles don't follow that logic. Instead, they can be in a state of superposition, existing in multiple possible states at once. Imagine a switch that is both on and off until the moment you check it. That's not an analogy. It's literally what experiments show about electrons, photons, and other quantum systems. This bizarre rule is why scientists built the concept of the wave function, a kind of probability map describing all the possible states of a particle. But here's the twist. The moment we measure the system, the wave function collapses into a single outcome. The particle is forced to choose. In everyday terms, it's as if reality only finalizes itself when observed. For a long time, this was brushed off as a quirk of physics too small to matter in the bigger picture. But today, we know that quantum mechanics isn't confined to the subatomic world. It underlies all of chemistry, materials, electronics, even the processes that allow life itself. Every piece of technology around you, your phone, your computer, even the lights in your house works because of quantum rules. And here's where it gets even stranger. The more scientists probed, the more they realized that quantum mechanics isn't just about particles bouncing around. It's about relationships, probabilities, and outcomes that only make sense when seen in the context of larger systems. In other words, the deeper you go, the less the world looks like a machine made of separate gears, and the more it looks like a web of interdependent possibilities. But if quantum mechanics rewrote our understanding of particles, how far can we take that idea? To find out, let's look at how physicists tried to extend reductionism into the quantum world and where it started to break down. To see how science built its picture of reality, let's rewind to the early 20th century. In 1934, Enrico Fermi proposed a theory to explain beta decay, the process by which a neutron transforms into a proton and an electron. His explanation worked well enough for decades. It treated the decay as a kind of direct interaction, a neutron simply splitting apart. But then, in the 1970s, a deeper layer was revealed. Physicists discovered the W and Z bosons, heavy particles that actually mediate the weak nuclear force, the interaction responsible for beta decay. Suddenly, Fermi's model was no longer fundamental. It was just an approximation of something deeper. This discovery shaped a new way of thinking, effective field theories, EFTs. Imagine a set of Russian nesting dolls. Each doll fits neatly inside the next, and each layer reveals more detail. That's how physics works. At one scale, a simplified theory can describe phenomena accurately. But peel back another layer, and you find a more detailed structure that explains what's really happening. The Standard Model of particle physics is the ultimate example of this nesting approach. It unites three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force into a single, dazzlingly precise framework. The Standard Model has been tested in experiments around the world, from particle accelerators to deep underground detectors, and it almost always gets the numbers right. But here's the problem. The Standard Model isn't complete. It leaves out gravity. It has no explanation for dark matter or dark energy, which together make up about 95% of the universe. And even within the Standard Model itself, strange puzzles remain unsolved. Puzzles that hint that reductionism, even with its nesting doll approach, may not be enough. This leads us to the next challenge in physics, a problem so glaring that it threatens to upend the entire framework scientists have relied on for decades. The Standard Model is often described as the most successful scientific theory ever created. It predicts particle behavior with astonishing precision. But despite its triumphs, there's a crack running through its foundation, one so big that some physicists call it a crisis. The heart of the problem lies in the Higgs boson. Discovered in 2012 at CERN's Large Hadron Collider, the Higgs gives mass to fundamental particles. Without it, electrons wouldn't have weight, atoms couldn't form, and chemistry, let alone life, would be impossible. But here's the catch. According to quantum theory, the Higgs boson's mass should be enormous, blown up to a value trillions of times larger than what we actually measure. Why? Because the Higgs doesn't exist in isolation. It interacts with a cloud of virtual particles, constantly popping in and out of existence thanks to quantum fluctuations. Each interaction should nudge the Higgs mass upward, adding corrections that would make it absurdly heavy. The only way its mass could stay small is if these quantum contributions somehow cancel out with mind-boggling precision. To put it in perspective, it's like balancing a pencil perfectly on its tip. Theoretically possible, but in practice so unlikely, it feels almost impossible. Scientists call this the fine-tuning problem. For decades, physicists hoped new theories would explain this. One idea was supersymmetry, a bold proposal that every known particle has a hidden, partner particle. These superpartners would cancel out the quantum contributions to the Higgs mass, solving the fine-tuning problem. Another idea was that hidden extra dimensions could reshape the math of particle physics, stabilizing the Higgs in the process. But here's the uncomfortable truth. After years of searching at the world's most powerful colliders, there's no evidence for supersymmetry or extra dimensions. The partners haven't shown up. The theories remain unproven. This absence has forced physicists to face a radical possibility. Maybe the problem isn't missing particles. Maybe the problem is how we're thinking about reality itself. Instead of trying to solve fine-tuning by finding smaller building blocks, perhaps the answer lies in understanding connections, the way the smallest and largest scales of the universe might influence each other. To grasp this new way of thinking, imagine a rainbow. At first glance, it looks like separate bands of color: red, orange, yellow, green, blue, indigo, violet. But in reality, the rainbow is continuous. Beyond violet lies ultraviolet radiation so energetic our eyes can't see it. Beyond red lies infrared waves too long for our vision. The visible rainbow is just a slice of a much larger spectrum. Physicists suspect something similar might be happening in reality itself. The smallest scales of the universe, the ultraviolet, or UV in physics language, and the largest scales, the infrared, or IR, might not be independent. Instead, they could be linked in subtle ways, a phenomenon some researchers call UV-IR mixing. If this is true, then the behavior of particles at unimaginably tiny distances could shape the very structure of the cosmos. And conversely, the way the universe expands and evolves on the largest scales might ripple back down, influencing what happens inside atoms. This idea is radically different from reductionism. Traditionally, we thought physics at different scales could be studied separately, particle physics here, cosmology there, but UV-IR mixing suggests they are entangled in ways we're only beginning to glimpse. And here's where things get truly fascinating. The key to understanding this connection may lie in quantum entanglement. Entanglement occurs when two particles become so deeply linked that their properties remain correlated no matter how far apart they travel. Measure one particle, and you instantly know something about the other, whether they're across a lab or across a galaxy. Einstein once mocked this as spooky action at a distance. But decades of experiments have shown it's real. If entanglement is not just a laboratory curiosity but a fundamental feature of reality, then it might be the hidden thread connecting the UV and IR. In other words, entanglement could be the glue holding the entire universe together, the mechanism that makes the cosmos more than just a sum of parts. But this raises a daring possibility. If entanglement stretches across scales and distances, maybe the universe itself isn't a collection of separate pieces at all. Maybe it's one single, unified quantum object. If entanglement truly connects everything, then what does that say about the universe itself? Physicist David Bohm challenged the reductionist worldview with a radical idea. Maybe the universe has a universal wave function, a single, all-encompassing quantum state that describes everything at once. Instead of billions of isolated particles interacting like billiard balls, reality might be more like a cosmic ocean, where every ripple affects every other ripple. Think of a drop of water falling into a still pond. Waves spread outward, but they don't exist independently. Each wave changes the whole pond. In Bohm's view, particles and fields are like those ripples, not standalone objects, but patterns in a much deeper, unified reality. This way of thinking changes everything. It suggests that what we call objects, atoms, stars, galaxies, even ourselves are not separate things but expressions of one underlying whole. The universe, in this picture, is a single, interconnected system. And there's more. Modern physics has started catching up to Bohm's intuition. In quantum field theory, particles aren't actually little dots of matter. They're excitations of fields that stretch across the universe. When you see an electron, what you're really seeing is a tiny vibration of the electron field that exists everywhere. In other words, the boundaries between things blur when you look deeply enough. Entanglement ties this together. If every particle field is linked through quantum states, then separation itself may be an illusion. Even space and time, the fabric we take for granted, could emerge from entanglement patterns. Some researchers today argue that space-time itself may not be fundamental, but is instead woven out of quantum connections. That's not just a metaphor. Cutting-edge studies in black hole physics show that the geometry of space might literally arise from how particles are entangled. Remove the entanglement, and space dissolves. In this sense, reality is not built from particles at all, it's built from relationships. This is a radical departure from reductionism. Instead of breaking reality down into ever smaller parts, it points to a universe where the whole comes first, and the parts are secondary. We're not separate from the cosmos, we are threads in its single quantum fabric. Here's where the story takes a provocative turn. If everything in the universe is entangled, if space and time themselves might emerge from quantum connections, then where does consciousness fit in? Physics has long sidestepped this question. Consciousness is messy, subjective, and notoriously difficult to measure. But some physicists argue we can't ignore it. After all, quantum theory itself raises a strange puzzle. Why does measurement matter? In quantum mechanics, a particle exists in a superposition, many states at once, until it is observed. Observation collapses the wave function into a definite outcome. But what counts as an observer? Is it a machine? A human mind? Or is consciousness itself somehow entangled with reality? This mystery has led some thinkers to revisit ideas once dismissed as philosophy. The theory of panpsychism, for example, suggests that consciousness isn't an emergent property of brains alone, but a fundamental aspect of the universe, present in some form everywhere. Just as gravity is woven into space-time, perhaps awareness is woven into the quantum fabric. Speculative? Absolutely. But it raises fascinating possibilities. If the universe is one giant entangled system, then consciousness might not be a byproduct of matter. It might be a feature of the universe itself, distributed across scales we don't yet understand. And here's the twist. Some modern research in quantum information hints at this connection. The way we describe entanglement mathematically often looks like the way we describe information processing, the very thing our brains are doing when we think. This overlap has inspired a daring question. Is the universe not just physical but also informational at its core? And if so, is consciousness simply the universe becoming aware of itself through us? We don't have the answers yet, but the fact that these questions are even being asked shows just how far we've moved from the neat, reductionist picture of the 20th century. The frontier of physics is no longer just about particles and forces, it's about meaning, connection, and maybe even mind. So what does all of this mean? For centuries, science has told us that the best way to understand the world is to break it into parts. Atoms, molecules, cells, planets. Each step down was supposed to reveal the ultimate building block of reality. But the deeper we've gone, the stranger the picture has become. Instead of finding simple, indivisible pieces, we've uncovered a web of connections, a universe where everything is entangled and nothing exists in true isolation. The Higgs boson showed us that mass itself is not intrinsic but arises from a hidden field. Supersymmetry and extra dimensions forced us to imagine realities beyond what we can see. Entanglement revealed that separation is an illusion, that a particle here can be instantly tied to a particle across the galaxy. And the idea of a universal wave function suggests that the entire cosmos is a single quantum organism, with each of us as expressions of its unfolding story. Even consciousness, long ignored by physics, is now creeping back into the conversation. Could it be that awareness is not something the universe accidentally produced, but something woven into its very fabric? That question pushes us beyond science as we know it, and into the edges of philosophy, maybe even spirituality. And yet, it's a question more scientists are daring to ask. This new vision of reality is unsettling. It means the universe is not a clockwork machine, ticking away according to simple rules. It is more like a living system, an ocean of relationships where the whole gives rise to the parts, not the other way around. And maybe that changes how we see ourselves. If we're not isolated observers but threads in the universe's quantum fabric, then every action, every thought, every connection we make echoes across the whole. In a very real sense, we are the universe, looking back at itself. The search for ultimate truth is far from over. Physics may still uncover deeper laws, stranger particles, or even other universes. But one thing is already clear. Reality is far more mysterious, interconnected, and alive than we ever imagined. And that leaves us with a haunting question. If the universe is one vast, entangled system, then what role do we play within it? Are we just fleeting ripples on the cosmic ocean, or something much more?